Calculating pH. pH is defined as the negative logarithm of the hydronium or hydrogen ion concentration. P always means negative log. So POH is the negative log of the hydroxide ion concentration. And from yesterday's assignment, pH plus POH equals 14. Because when you take a log of a product, it's the sum of the logs. One of the things you're going to have to do is fill in a table with hydrogen or hydronium ions, hydroxide ions, pH, POH, and is it an acid, a base, or neutral? You'll be given some things like 1 times 10 to the negative third, and maybe a POH of 5. And then you have to fill in the rest of the numbers. Remember that the hydrogen ion and the hydroxide ion has to multiply together to give you 1 times 10 to the negative 14th. If it's 1, then it's always going to be 1, so it's 1 times 10 to the negative 11th. The negative logarithm of 1 times 10 to the negative 3 is 3. Remember, logs are exponents, so plug that in your calculator, or if it's 1 times 10 to the power, then it's just the exponent. That would give you a pH of 3, and then a POH, which has to add up to be 14, of 11. And that makes it an acid. Well, if this is a pH of 5, POH of 5, that would make this a pH of 9. 9 plus 5 is 15. These are whole number problems, so you'd have to take it to the negative exponent. So it's 1 times 10 to the negative 9. Logarithms are exponents. If the exponent's 9, then that's what the exponent is for the negative in front of it. Same thing for the POH. You can make that 1 times 10 to the negative 5. 9, negative 9, negative 5, that has to be negative 14. Now, if one of these values was not 1, you'd have to use your calculator. 1 times 10 to the negative 14th divided by this would give you that number. The negative logarithm of this would give you the POH and whatnot. Here the pH is greater than 7, so this would be a base. How to calculate the pH of strong acids? Here the 4 strong acids are hydrochloric acid, sulfuric acid, nitric acid, and perchloric acid. Those are the 4 strong acids. And you have to know, just memorize them. Strong acids ionize completely. They do not form an equilibrium. So if you have 0.01 molar hydrochloric acid, that will fall apart to give you 0.1 molar hydronium ions or hydrogen ions, either way. Negative log of that, pH equals 2. There is one exception to this, and that is if your concentration of your strong acid is less than 1 times 10 to the negative 7. If that's true, then the water is going to be a stronger acid, and it's going to give up more H plus. So the pH of a strong acid will never go above 7. Which makes sense, because it's an acid, it shouldn't have a base when you go that way. So the pH will never go above 7 if you have a strong acid in very weak quantities, less than 1 times 10 to the negative 7. Well, we have the pH of strong acids, now we have the pH of weak acids. These ionize partially, usually less than 5%. And since it's less than 5%, we can do the assumption where any addition or subtraction of an X is ignored. Let's say we have some strong acid, say generic HA. It will react with water, which is a liquid, to form an equilibrium with H3O plus, the hydronium ion, plus the anion. The concentration of the HA is the generic HA. Water we can ignore, initially 0 and 0. We're going to subtract X and add X and add X, because you cannot remove from 0. So this concentration of HA minus X, this is X and this is X, but with the assumption we can ignore that. That's only if the Ka is greater than 1 times 10 to the negative 4. If it's 1 times 10 to the negative 3 or 5.2 times 10 to the negative 2, then that is not permissible, and you have to do it the long way with the quadratic formula and such. So we have Ka equals X squared divided by concentration of HA. And it's only true if you have one contributor to the hydrogen ions. If you have 2 contributors to the hydrogen ions, then we've got to cover that later on. Specific example, 0.5 molar HCOOH with a Ka equals to 2 times 10 to the negative 6. What is the pH? Well, this is less than 1 times 10 to the negative 4, so we're good with the assumption. Now you can set up the table if you wish, or you can kind of just jump in with this formula. I do strongly suggest Ka, writing up the equilibrium, just in case something funky happens. HCOO minus HCOOH. Okay? Some people just say, go ahead with this and don't do any assumptions. Don't jump to X squared over 0.5, 2 times 10 to the negative 6. The vast majority of the time you're going to be fine with this, but occasionally you get tripped up by that. Cross multiply, 1 times 10 to the negative 6 equals X squared. Square root both sides, X equals 1 times 10 to the negative 3, negative log of that, pH is equal to 3. Okay. Now a complication. You're going to have 2 acids. So to the above situation, you put in 0.2 molar, let's call it HX, where Ka is equal to 1 times 10 to the negative 8 is also present. It's not just the HCOOH, but the acid HX. This is going to be just like we did up here with the water situation. The stronger acid is going to contribute all the hydrogen ions. So this is going to be the hydronium ions. This is going to be the pH. So everything else is going to be the same. So the hydronium ion concentration is 1 times 10 to the negative 3, and the pH is 3. But if you're also concerned with trying to find the concentration of the anion, of the weak anion, you have to go back to the Ka. Ka equals concentration of H3O plus times concentration of the anion divided by the concentration of the weak acid. Now, this is a case where you cannot have X and X, because this is your concentration of the H3O plus. You have to plug that in. When you do that, you have to go ahead and figure out with only one X, unknown. So it's 1 times 10 to the negative 8 equals 1 times 10 to the negative 3 times the concentration of the anion divided by 0.2. Cross multiply, solve for concentration X squared, and you get that. I don't have that for you. Okay. The last thing is the formula for finding the percent dissociated. This is how much of the weak acid has fallen apart. And it is the amount dissociated, which is the hydronium ion concentration, divided by the initial amount of the weak acid. For up here, for the above, 1 times 10 to the negative 3 is the hydrogen ion concentration, divided by 0.5, which is the initial concentration, equals 0.002 or 0.2%, which is less than 5%, so you can use that assumption. That proves it's less than 5%, so we're good to go. Back up to here, this X, what is X? X is both the hydronium ion concentration and the anion concentration. So this X is not just the acid part, it's also the anion part. That concludes this lesson on calculating pH.